Okay, 6.2, the binomial probability distribution. In 6.1, we stated that probability distributions could be presented using tables, graphs, or mathematical formulas. So in this section, we're going to introduce a specific type of discrete probability distribution that can be presented using a formula, right? It's the binomial probability distribution. And that is a probability distribution that describes the results for experiments in which there are two mutually exclusive outcomes. Right? So here's the criteria for a binomial probability experiment. 1, the experiment is performed a fixed number of times. Each repetition of the experiment is called a trial. 2, the trials are independent. This means, remember, the outcomes of one will not affect the outcome of the others. For each trial, there are two mutually exclusive outcomes, either success or failure. Okay, so success doesn't necessarily mean anything positive. It just means, yes, the probability occurred of whatever you're asking about, right? Also, being two, and that's what by, the prefix by means. So maybe that'll help us remember that these are the requirements for the binomial, okay, probability. So the probability of success is fixed for each trial of the experiment. Okay, here's our notation. There are n independent trials of the experiment. P is going to denote the probability of success, so that 1 minus P is the probability of failure, right? Mutually exclusive complements. Okay, so capital X will be the binomial random variable that denotes the number of successes in independent trials of the experiment. So X has to be between 0 and n, inclusive, where, remember, n is the number of trials. Okay, so which of the following are binomial experiments? A player rolls a pair of fair die 10 times. The number X of sevens rolled is recorded. The question is just, is it a binomial experiment? So let's check those 4 requirements. It's performed a fixed number of times. Yes, 10 times. Okay, so check on number 1. The trials are independent. Yeah, we're rolling dice, so the second row has nothing to do with the first row or the third row. Check independent. There's only 2 possible outcomes. Okay? Yes, either you got a 7 or you didn't. Okay? And the probability of success for each trial is constant. Yes, the probability of getting a 7 is 1 out of 6 in every single trial. Well, not if you're rolling a pair, but let's just, to keep it simple, let's make it 1. It's 1 die. Okay, so yes, that is a binomial experiment. Okay, what about B? The 11 largest airlines had an on-time percentage of 84.7% in November of 2001, according to the Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flights until she finds 10 that were not on time. So the number of flights, X, that needed to be selected is recorded. All right, let's check our 4 conditions. Is the experiment performed a fixed number of times? No, right away I know it's not binomial because she checks flights until she finds 10. We don't know how long it's going to take her to do that. Okay, so it's not that she looked at 10 flights, right? She's checking flights until she finds 10 not on time. Not binomial. C. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. Okay, Is the experiment performed a fixed number of times? Okay, yeah, it's going to select 4 students. Okay, are the trials independent? Oh, no, there's only 30 students. And so once she picks a female, the probability of that next female changes, right? Can't use the law of large numbers here. It's only 30, not binomial. Okay. All right, here's an example. Let's construct a binomial probability distribution. Okay, so according to the Air Travel Consumer Report, the 11 largest air carriers had an on-time percentage of 79% in May 2008. Suppose that 4 flights are randomly selected from May, and the number of on-time flights, that's our variable, is recorded. Construct a probability distribution for the random variable x using a tree diagram. Okay, and so they've already constructed the tree diagram for us, but let's go over it in case we need to construct one ourselves. Okay, so 4 flights are randomly selected. So here's the first selection, the second, the third, the fourth. Okay, so on the first, there's either a success or a failure. Either means it was on time or it was not on time. Okay, so in the second trial, right, if the first one was on time, then it's possible that the second one was also on time, but it's possible that it was not. Same thing down here. If the first one was not on time, the second flight could either be on time or not on time. Okay, now for the third trial, no matter what happened on the second, whether you had 2 successes, you could have another success. Or whether you had a success and a failure, you could have a success. You could have another failure. Okay, if you had a failure and a success, you could have a success. If you had a failure and a failure, you could have a failure. Okay, so for each trial, it adds 2 more options, right? So, and here's all your outcomes. All 4 of them could have been on time. The first 3 could have been on time, and the last one not. You could have had 2 on time, not on time again. 2 on time, 2 not on time. On time, not on time, on time, right? And to get those, you just follow each path, right? Each path. Okay, and then they counted the number of successes. So in this one, 4 successes, and this one, 3 successes, right? 3 successes, 2. Here's another way you could get 3. Here's another way you could get 3. So now what we need to do, we're going to create a probability distribution. Let me get my pen. I'm trying to think of how I'm going to fit all this in the room that we have here. So our probability distribution looks like this. Remember what it looks like from before. Okay, where we've got x, and then our probability will go over here. So let's see how many options we have. Okay, we have a 0, 1s, 2s, 3s, and 4s. So that's our variables. Okay, and we've just got to calculate all these probabilities. So let's see how we can do that. All right, let's start up here with the 4. And it tells us the probability that you were on time, that you had a success, is 79%. So the probability that we had all 4 of them on time is 0.79 times 0.79 times 0.79 times 0.79, right? 1, 2, 3, 4, and they were all successes. So let's say that's 0.79 to the 4th. Okay, 0.389 0.3895, rounded to the 4th decimal place. Okay, now let's look at the probability that we had 3 successes. So notice this one, this one, this one, this one. That's how many ways you can have 3 successes. So in the first one, we've got a 0.79, 0.79, 0.79 times now success, 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 failure. So 1 minus 0.79, what's that, 0.21? Okay, but then we've got to say plus this probability that it came in this way, 0.79, 0.79, 0.21, 0.79, right? Plus 0.79, 0.21, 0.79, 0.79, plus 0.21, 0.79, 0.79, 0.79. Okay, so I have to add up all the probabilities in the way that you can get 3 successes and 1 failure. Okay, so this is, let's notice what this is as we add it up. Look, I'm adding up 4 rows, but all of them have 0.793 times. They might be in a different order, but they all have 0.793 times, and I've got 4 of them. So 4 of them times 0.79 cubed times 0.21. Okay, just an easy way to enter it in our calculator. So 4 times 0.79 cubed. Wait, the 4 didn't go in. 4 times 0.79 cubed times 0.21. Okay, so 0.4142. Okay, and now I've got to do the 2's. Notice there's 4 of them also. So I'm going to put 4 times, and in each one, let's look at the 2's. There's 2 failures and 2 successes. 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 So times 0.79 squared times 0.21 squared. So 0.1101. Okay, and now for the 3's. No. Oh. Shoot. All right, I'm going to fix that easy enough. Easy enough, right? Because I started up here with the 4's and then did the 3's and the 2's. Okay, so now we're to the 1's. Okay, Here's a 1, here's a 1, here's a 1, and here's a 1. Just a coincidence that there's 4 of these every time. We'll look at that in just a minute, right? So this time it's going to be 4 times, now let's look at the ones. There's 3 failures and 1 success. That's what the 1 is telling us, right? 3 failures and 1 success. So times 0.79 times 0.21 cubed, which is 0.0293. And then there's only one time that it comes in 0, and it's if they're all a failure, so 0.21 to the 4th. So 0.0019. So there is our probability distribution for a binomial, right? A binomial probability distribution. Okay. Now, think about what we've been noticing about an easy way to calculate these things, right? What that actually is, okay? Think about this and how we did each one until we get to the next slide. Look, okay, the probability of obtaining X successes in N independent trials of a binomial is given by, ours was a 4, it was a 1, and then it was a 4 for the rest of the time. That number can be obtained by the number of trials. Choose whichever one you're talking about, right? Times the probability, times the complement of that, right? 1 minus the probability. Notice X times N minus X. Okay, so really now we've got a little formula to use. Okay, when we're reading probability problems, pay special attention to key phrases. And here's some examples. Okay, I wish they'd had this in a little bit better table with some lines between it. But at least, no less than, greater than or equal to. All of those equate to this symbol mathematically. More than or greater than, I'm going to draw some lines in here for us, so you may want to do the same on yours. Just to keep them straight. Okay, exactly, or equals, or is, that's an equal sign. No more than, or at the most, or less than or equal to, right? Looks like this. Okay, fewer than or less than, looks like this. More than or greater than, like this. Okay, so according to the Experian Automotive, 35% of all car-owning households have 3 or more cars. Okay, in a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? Now, it has told us it's a binomial probability distribution, but if it doesn't tell us, I need to go through that, those 4 checkpoints and make sure it's a binomial probability distribution. We can assume that on these, but we've already been through how do you know if it is. And because it is a binomial probability distribution, then I know, now this one says exactly. I know how to find the probability that 5 is going to happen, right? Okay, remember the formula from before. It was N, choose X. So 20 is our N. Choose 5. Okay. It says 35% of all car-owning households have 3 or more cars. So this is 0.35. That's our probability. okay, to the x. And then 1 minus 0.35 is 0.65, okay, to the 20 minus 5, so 15. There it is. And I can plug that in my calculator. Let's see what it is. 20 choose 5 times 0.35 to the 5th times 0.65 to the 15th. Okay, so 1272. Okay, in a random sample of 20 car-owning households, what's the probability that less than 4 have 3 or more cars? Okay, so let's think about that. Let's do the probability. So this is x is less than 4. Notice that's the same thing as saying less than or equal to 3, right? So either of these would be the same thing. All right, which that just means then I have to do this, and since it just asks exactly 5 less than or equal to 3, well, then I've got to do it for 0, for 1, for 2, and for 3. Okay, so this is going to be a long one. Okay, so 0, 20, choose 0 times point. Let me try to, hate this when I don't have enough room. Try to do it up here so I can fit it in. 20, choose 0, okay, times 0.35 to the 0 times 0.65 to the 20. And I'm just plugging into that formula we had on that, previous slide. Okay, so there's the 0 one, plus I need to add the probability of 1 success, so 20, choose 1, times 0.35 to the 1, times 0.65 to the 19, okay, plus 20, choose 2, times 0.35 squared times 0.65 to the 18, plus 20, choose 3, times 0.35 cubed times 0.65 to the 17. Okay, and I've got to enter all that in my calculator. Okay, so what I'm going to do to get me going is I'm going to hit second enter, so that from before will just enter in. I won't have to continually enter the same thing over and over. Okay, so I'm just going to go in and change that 0, that 5 to a 0 from what I had earlier, and then 0.35 to the 0, that's 0.65 to the 20th, okay, and then I'm going to have a plus, I've got to start all over. Sorry, I hit the wrong key on my calculator. So now, all right, so we're going to enter all of that. So 20, choose 0, times 0.35 to the 0, which really is 1, so 0.65 to the 20th, plus 20, choose 1, times 0.35 times 0.65 to the 19th plus 20, choose 2 times 0.35 squared times 0.65 to the 18th plus 20, choose 3 times 0.35 cubed times 0.65 to the 17th. Okay, so 0.0409. All right. In a random sample of 20 car-owning households, what's the probability that at least 4 have 3 or more cars? Okay, at least 4. Let's think about this. The probability at least 4, that's greater than or equal to 4, right? So 4 or more. So just think about this. If there's 20 of them, I could do all of this for 4 plus 5 plus 6 plus 7 plus 8. Imagine, think about what a pain this was to put in our calculator. Imagine having to enter 16 separate entries, okay? Or, hey, let's use our complement rule. Look, this is less than or equal to 3, greater than or equal to 4. Altogether, that's 1, right? So I should just be able to do 1 minus 0.0409. .9591. So don't forget about those rules that help us to do things. Yeah, I could have gotten the correct answer if I didn't make a mistake, hit the wrong key in my calculator, which is so easy to do. So think about what makes things easier for us. All right, so just having a nice formula. Let me know if you need anything. Okay. Now, let's see if we can obtain a binomial probability using technology. Oh, yay, awesome, right? So according to the Gallup organization, 65% of adult Americans are in favor of the death penalty for individuals convicted of murder. In a random sample of 15 adult Americans, what's the probability that exactly 10 favor the death penalty? Okay, so it's an exactly, so I only have to do 1. Let's see if our calculator can do that. Now, again, it's telling us it's a binomial. You got to make sure it's a binomial. And the instructions for this is in your technology tips from the text, okay, module. So I'm going to hit second and go into the VARs, not the stat, second VARs, because notice right above it, it's distributions, right? So we have lots of distributions in there. Scroll all the way down until you see the one that says binomial. Actually, it says binom, but binomial PDF. Binomial probability distribution function. All right, and I'm going to select that. And then my N, my number of trials, okay, a sample of 15, comma, okay, my probability, 0.65, probability of success, comma, and then X, what I'm talking about. In this case, 10. And hit enter. And I got 0.2123. Okay. Now what about this one? It says no more than 6. No more than 6. So this is the same thing as a probability that X is less than or equal to 6. Okay, remember when we were doing this before by hand, I would have had to have done 0, 1, 2, 3, 4, 5, and 6. Okay, let's go back into that distribution. So second VAERS, and notice right below you've got a binom CDF, binomial cumulative distribution function. So it'll accumulate all of your values for you. Okay, so I'm going to choose that one. And then we put our n, there's still 15, comma. Okay, this time whatever number you want that's less than or equal to. So you might have to adjust until you can come up with this, right? But this one is 6. And no, put your probability first, sorry. 0.65, thought we already had it in there till I looked down. Okay, and then the 6. Okay, and that is 0.0422. All right, technology. Did you love it? Okay. Okay, we discussed finding the mean and standard deviation of a discrete random variable already. And these formulas can be used to find the mean and standard deviation of a binomial random variable, but there's a much simpler method, like this. Okay, if it's a binomial, right, with n independent trials, probability of success p, then here's two simple formulas for your mean and standard deviation. Okay, so let's make note of those and do an example. According to the Experian Automotive, according to the Experian, maybe that should just be according to Experian Automotive. Okay, 35% of all car-owning households have 3 or more cars. In a simple random sample of 400 car-owning households, determine the mean and standard deviation number of car-owning households that will have 3 or more cars. Okay. So the mean is simply n times p. Seriously, that simple. 400 times 0.35. So 140 of them, on average, will have 3 or more cars. Okay, standard deviation is the square root of NP times 1 minus P. Okay, well, we've already found NP, so let's just put that in there, 140. And 1 minus P, if P is 0.35, 1 minus P is 0.65. So the square root, 140 times 0.65. 9 point, and let's see, so let's round to 1 decimal place, 9.5. Awesome, right? Oh yeah. Okay, to graph a binomial probability distribution, we first have to find the probabilities for each possible value of the random variable. Okay, and then we're just going to do the same thing that we did to graph the other, discrete probability distributions. Okay, so this one says graph the binomial probability distribution with n equals 8, p equals 0.15, comment on the shape of the distribution. Notice, look, these say exactly the same thing. The only thing that's different is p equals 0.15, p equals 0.5. Okay, so we're going to look at what happens as our p's change. Everything else the same. Everything else exactly the same. Okay, so the first thing we got to do is find our probability distribution table. And I know that diagram is there, but let's see first how we would get it in reality. Okay. Now, it's n equals 8, right? So I will have x, and we'll have 0, 1, 2, 3, 4, 5, 6, 7, 8. And now that we know our calculator will do this, we're actually just going to use our calculator to get these values. All right? All right. So remember what we had to enter in. Okay? So we're going to do 0 first. And the n is 8. So we're going to do 8, choose, let's see, 0. Okay, sorry, having a calculator issue. Okay, times 0.15 to the 0. And I'm going to go ahead and enter that, even though I know that's 1. Actually, I know what 8 choose 0 is also, but we'll see why. Times 0.85, right? And that came from 1 minus 0.15 to the 8th. Okay, so we got 0.2725. Okay, now hit I've got to fill out every one of these. Just hit second enter. And you can go back and get a 1, change the 0 to a 1, and the 8 to a 7. Okay, 0.3847. Okay, then hit second enter again and just go in and change those values that change. So I'm going to make that a 2, make that a 2, and now I've got to make this a 6. Okay, 0.2376. Okay, and now let's second enter and make that a 3, and a 5. 0.0839. Okay, and let's do, I'm going to just do, for the sake of time, one more. Change those to a 4, and then that last one, we'll change everything to a 4 this time. 0.0185. Okay, so that's how you would get your table, your probability distribution table, right? And then you'd graph it just like we have talked about in previous, right? Here's our x and here's our p of x, or our frequency. Now, it says comment on the shape. So let's look at the shape. Okay, it appears to be skewed right. Okay, it is skewed right. Okay, then it asks you to do it again, except p is 0.5. So we know how to get the table if we needed to. And here's the graph of it. Comment on the shape. Oh, it looks bell-shaped, right? Looks symmetric. Okay, here's the next one with p.85. Oh, it is skewed left. Okay. So what that means is if p equals 5, you get a bell-shaped distribution. If, not 5, 0.5, you get a bell-shaped distribution. If p is less than 0.5, it's going to be skewed right. And if p is greater than 0.5, it's going to be skewed left. Okay? So that's going to be important for us. In addition to that, let's see what happens with n, right? If we change n. Okay, so here it says graph the binomial probability distribution when n is 25, p is 0.8. Comment on the shape. Okay, so the only thing we're going to be changing now is n. All right, so sort of, it's a little bit skewed left, maybe, right? A little bit skewed left. Okay, here's the same thing with n50. Oh, it's pretty symmetric. Here it is with n70, more symmetric, more bell shape. So we're going to conclude, right? For a fixed p, as the number of trials increases, the probability distribution of the random variable becomes bell-shaped. That's basically our law of large numbers that we just talked about earlier, right? As the number of trials increases for a large number of trials, okay, then we can assume that it's going to be bell-shaped. Okay, how large a trial? Well, here we are. As a rule of thumb, if n times p times 1 minus p is greater than or equal to 10, the probability distribution will be approximately bell-shaped. Okay, so the usefulness of that is this allows us to use the empirical rule to identify unusual observations in a binomial experiment. Remember, this was also, we could call it our 68, 95, 99.7 rule. What the empirical rule states is that in a bell-shaped distribution, about 95%, that's our middle number, of all observations lie within 2 standard deviations of the mean. In other words, 95% of the observations lie between mu minus 2 sigma and mu plus 2 sigma, right? Remember, we did this. Okay, so we're going to say that any observation that lies outside this interval, more than 2 standard deviations, is going to be considered unusual because that means it's going to occur less than 5% of the time. All right. So, according to Experian Automotive, 35% of all car-owning households have 3 or more cars. A researcher believes this percentage is higher than the percentage reported by Experian Automotive. So he conducts a simple random sample and found that 162 had 3 or more cars. Is this result unusual? All right. Well, we need our mean and standard deviation to see. Okay, so the mean is 400 times 0.35, and if I recall from a while ago, that was 140. I better check myself, but that's what I remember getting. Right, okay, and standard deviation is the square root of 140 times 0.65, 1 minus p. I don't remember what we got for that, so let's plug it in again. Okay, 9.5. Oh yeah, I remember that now. All right, so here's what we're looking for. I want to know what is mu plus or minus 2 sigmas. Okay, so 140 plus 2 times 9.5. So 140 plus 18, 158. And I want to know what mu minus 2 times 9.5 is. So 100, oh, that's a 9. 19, two of those would be 19. Sorry, guys. I always check the work I do in my head. Always double check me on that. Okay, so 140 minus 19 then, or 121. Okay, and he found 162. That's more than 159. So, yes, I would say that's unusual because 162 would only happen less than 5% of the time. All right, that finishes up chapter 6, which means you have a test coming up now. So let me know if you need anything.